All right, we've talked about how to do the classification of a chemical reaction. So we've learned how to identify what type of reaction it is, right? So we can figure out whether it's synthesis or decomposition or single replacement or double replacement or combustion. Now, that is assuming you have the entire reaction given to you and you're looking at the entire reaction. Can you tell what type of reaction it is? And that's something you should be able to do by now. But one of the other things that we should also be able to do in here is predict what the products would be of a chemical reaction. So if you were given just the reactants, could you predict what the products were going to be if you could tell what type of reaction it was? So we're going to do just a little bit of practice with that. So we're also going to review the types of reactions real quick, because if we can figure out the type of reaction from just the reactants part, then we can have a good chance of predicting what the products are going to be. So we're going to start back with synthesis again. Remember, synthesis reactions, sometimes called combination, but generally we don't use that term very often. Synthesis reactions is where we have two or more reactants that make one product. Now, there are other reactions that have two or more reactants in them. So just telling from the reactants themselves is not always an easy thing to do. So I've got some common synthesis or combination reactions that we can kind of look at, and this will give us a pretty big clue as to whether we're looking at a synthesis reaction or not, and how to figure out what the products are going to be. So one of the first things we can look at is if these two reactants here are a metal and a non-metal, just a plain old metal and a plain old non-metal here, there's a really, really good chance it's a synthesis reaction and it's going to produce an ionic compound. Now, how do we know what ionic compound is going to come from these two? Well, if we determine what charges these two would normally be, we could crisscross and come up with our formula for ionic compound. If the two reactants that are here are a non-metal and a non-metal, again, just a plain old singular non-metal and non-metal, then those two generally will form a molecular compound, right? Because non-metals and non-metals make up molecular compounds. Now, what would the formula be of a molecular compound? You know, we can't use crisscrossing in charges when we talk about covalent. So how do we do that? Well, this part here is where you need just a little bit of experience. You need to have some idea in your head of some common molecular formulas that go along with those nonmetals. Like, for instance, let's say that one of the reactants here was hydrogen and the other one was oxygen. Well, if you have hydrogen and oxygen and you need to figure out what molecular formula can you make from both of those, you need to think, what's a common compound out there that has hydrogen and oxygen in it? And probably the very first thing that comes to your mind and most people's minds would be water. Water has hydrogen and oxygen in it. And so you would go ahead and say, okay, I think it's going to turn into water. 95% of the time, you'd probably be right. Okay, so that one's a little bit trickier. And we'll go through some of the common molecular compounds at a later date. It's also possible that you have two reactants. The first reactant is a non-metal oxide, and the second reactant is water. If you ever see non-metal oxide and water together as reactants, they are always going to synthesize to make an acid. So non-metal oxide, that means that you have a formula that starts with a non-metal and ends with an O of some kind. And then, of course, water is H2O. So if you see that, you know those two are going to come together to form an acid. Now, how do you know what formula the acid's going to be? Well, remember, acids always start with H. And then they're going to end with the non-metal and O. But how many of each? What's that rest of that formula going to look like? And how many H's do you put in? Well, again, you're going to have some idea of some common acids in your head so that you know. And this is all from experience. If you practice this enough, you start to realize, oh yeah, I've seen that acid before. I've seen that acid before. I've seen that one before. The last common synthesis reaction that you're going to see out there is if one of the reactants is a metallic oxide and the other one is water. Anytime you put a metal oxide and water together, you get a metal hydroxide. Now, we know what hydroxide is, right? Hydroxide is a polyatomic ion. It's OH negative. And of course, the metal comes from the metal oxide, whatever that metal was. And we can figure out what its charge would normally be. And then we can crisscross them together. So essentially what we're making here is a base, right? A metal hydroxide is also known as a base. And bases are just ionic compounds. So we just use charges to put them together. So out of the 4 of these, all right, the first one here, metal and nonmetal make an ionic compound, is probably the easiest thing to do. The second easiest is probably the metallic oxide and water making a metal hydroxide, because again, all it requires is, if you know the charges, you can crisscross them together. B and C take a little bit more experience to figure out, but again, we'll do just a few of those. Those aren't going to come up very often, but if we do a few of those, you'll see how that works. All right, so let's do a practice one together to show how this would work. On the picture on the left, we have 2 reactants we're going to put together, iodine and zinc. Okay, so we're going to put iodine and zinc together. So they put them both together into this Erlenmeyer flask, and you see what's happening, right? You see there obviously is some kind of reaction happening. We have this purple gas that's starting to form in here, and we have lots of different changes that are happening, color changes and whatnot. So we want to write out what this reaction looks like, but they didn't tell us what the product is, right? So we want to figure that out. So first we're going to do is write out the 2 reactants. So I know I have iodine. Now why is iodine written as I2? Because it's a diatomic molecule. Remember, there's those elements on the periodic table that always form diatomic formulas. Right? We said there were 7 of them that you had to memorize. Iodine is one of those. And then we're putting that together with zinc. And then we're going to put our arrow because we know we're going to form a product. All right, so this is a synthesis reaction, right? And I have a non-metal and a metal, right? Iodine's a non-metal, zinc's a metal. So metal and non-metal might make ionic compounds. So what ionic compound are we going to make from this? Well, this is where we're going to have to do a little of our figuring out our charges. So I'm just going to do this up at the top here, sort of as some work off to the side. So let's start with zinc. Zinc's the metal. Metals are always positive of some kind, and zinc is one of those that I had to memorize as always being positive too. Iodine, now notice I'm not going to write the 2 with the iodine, because I just want to figure out what iodine by itself's charge is. Anytime I'm doing crisscrossing, I'm looking at individual elements by themselves, and then I'll crisscross them together to figure out how many I need. So iodine's in group 17. It's always negative. So if I have Zn positive 2, and if I have iodine that's negative 1, and I crisscross them, that tells me that my formula for my ionic compound is going to be ZnI2. The last thing I would do is I would make sure this is balanced, right? So if I go through and I balance this, it turns out everything works out all right, right? I have 1 Zn, I have 1 Zn, I have 2 I's, I have 2 I's. Everything is balanced. I don't need to do anything special to balance this. Now let me point out a couple of things. First off, right? How did I know this was going to be synthesis reaction? Well, all I have is an element, right? Just iodine, and another element, just zinc. What can I do with just 2 elements? This is the only thing I can do with just 2 elements, is synthesis. The other thing I want to point out, hey, this here, knowing their charges, is still important, right? That's not going away. If you're constantly resisting the idea of learning the charges and learning formulas and memorizing things that I've asked you to memorize, this is going to continue to get harder and harder and harder on you as we go. Don't make your life harder. I know it takes a little bit of time to memorize things. I realize that. It's not easy, but I guarantee you it's easier than constantly being lost every time we're doing problems for the rest of the year in here. Okay, next. Decomposition reactions, right? So decomposition reactions is just the opposite of a synthesis reaction. So we have one reactant this time, and it splits into 2 or more products. So this one's really easy to spot because it's the only type of reaction we talked about that starts with just one of the reactants. So we'll be able to spot this really quickly. How do we split it, though? How does it get split up in its products here is really just a matter of learning your synthesis reactions and doing them in reverse, right? Common decompositions are really just synthesis reactions in reverse. In fact, you can see that when you look up here, if you just did this reaction backwards, it would be a synthesis reaction. So we just learned 4 common synthesis reactions, right? We just learned that metal and a nonmetal makes an ionic compound. Non-metal makes a molecular compound. Non-metal oxide and water makes acids. And metal oxides and water make bases, metal hydroxides. So for those 4, if you run them in reverse, you can figure out how to split your reactant. So for instance, let's say that I was giving you an acid, and that's it. That was your only reactant. It was an acid. Well, if you have an acid as your reactant, if I go backwards from my synthesis, an acid then would turn back into a non-metal oxide and water. Right? That's how I should split it. So this is the idea of taking one reactant, splitting it up, and thinking of it just as a reverse synthesis. The other thing that I want to point out for decompositions is most decompositions are not natural processes. They're not things that just happen on their own. They generally need help. Some kind of energy needs to be added in. So a lot of times decomposition reactions will require some kind of either heat to the reactants, or some kind of special light shining on the reactants, or in some cases electricity given to the reactants to make them split, to make them decompose. Water is a great example of this. Water, which of course is made out of hydrogen and oxygen, doesn't split into hydrogen and oxygen unless you give it some kind of very particular energy, in this case, electricity. In fact, this is called the electrolysis of water. This is one of the reactions that we're going to look at in our lab later on. So if you pass electricity through water, you can get water to actually decompose into hydrogen and oxygen. All right, single replacement reactions. You remember single replacement reactions where we're just switching one partner. So we have an individual element plus a compound now. Okay, so the compound has 2 parts, usually 2 ions. And so we have an individual element that's going to go in and is going to replace one of these 2 ions and kick it out. So in this example here, this T, whatever this is going to go in and replace whatever this one is, the R, and kick it out. Now there's another, let's go back to this. There's another version of this, and if you look closely, there is a difference here. What if this element here is replacing the second one in these two and kicking it out, right? So this one could either come in and replace the first one, or could come in and replace the second one. How do you know which one it's going to replace? All right, well, this is where you need to think about what this element is. So if this element here, oh my, always got to have this problem. If this element here is a metal, metals can only replace other metals. So if this right here is ionic, and it usually is, an ionic compound always starts with a metal. So in this case, the metal would go in and replace whatever this metal is and kick it out. Okay? But if this beginning element here, if this one is a nonmetal, then nonmetals can only replace other nonmetals. Well, again, if this is ionic right here, where is the nonmetal? The nonmetal would have to be the second one. Always is in an ionic compound. So the nonmetal here would go in and replace the nonmetal here and kick it out. Now remember, metals are always the positive ions. They're always the cations. Nonmetals are always the negative ions. They're always the anions. So this is a cation replacing a cation. So we call this cationic single replacement. And this here is an anion. So an anion replacing another anion is anionic single replacement. Anionic single replacement. So those are important terms. In fact, in your homework, you're going to have to make sure that you're stating whether a single replacement reaction is cationic or anionic. Now, there's a few things that we have to remember about a single replacement reaction. Okay. It's relatively easy to figure out what the products are going to be because once you've identified whether it's going to be cationic or anionic, you know what's going to replace what. But to figure out if the replacement can actually happen or not, we have to use something called an activity series, and I'll show you what that looks like in just a moment. And we also have to remember that most replacements take place in aqueous solution. Now, why is that? Well, ionic compounds are made up of two ions that are attracted to each other. Normally, you couldn't get them apart from each other. But if they're dissolved in water, then they're already apart from each other. Okay? Because anytime you dissolve an ionic compound in water, the ions actually get pulled apart by the water. And then this guy can swoop in and replace one of them pretty easily. All right, so this activity series that I'm talking about looks like this. This is actually posted on Google Classroom. You may even have a paper copy of it. The activity series is a listing of metals, and the metals are listed in order of their reactivity. That's what we call an activity series. What does reactivity really mean? Well, it means how often do they really want to react and replace something else. So according to this, lithium is at the very top of this. Now, this is not every metal on the periodic table. This is just a lot of the common ones. Lithium is at the very top of this periodic table, which tells us that lithium is always wanting to go and replace another metal that's already in a compound. So in other words, if lithium is by itself, it doesn't want to be by itself. It would rather be with something else in a compound. But way down here at the bottom of this list of metals is gold. So that's telling us that gold almost always would rather be by itself than reacted with others. So if gold is in a compound, then it's probably going to get kicked out right away. But if gold is already by itself as a singular element, it's going to stay that way. And so what this list gives us is a clue as to whether one metal can replace another metal based on its reactivity. Even at the bottom here, it does show us that we could also do this with halogens. Remember, halogens are nonmetals, but halogens have their own activity series, and you can see them at the bottom here, right? Fluorine is the most active of the halogens. It would rather be in a compound. Iodine is the least active. That means it probably doesn't need to be in a compound. It's fine being by itself. All right, so let's do an example, right? Kind of practice how this would work. All right, so here's our setup. Got some copper metal here. Copper metal has a wire, right? It happens to be a copper wire. So we have solid copper metal that's being wound around this holder inside of this box. And then the box has been filled with a silver sulfate solution. So I have silver sulfate, the compound silver sulfates, dissolved in the water in this box. And then I let them sit for a while. Okay? And if you let this sit for a while, and you come back later and you look, notice all of the changes that have happened inside of here. There's a lot of changes. Right? In fact, there's a couple of big ones. We can see that the solution went from being basically clear, because remember the background behind is gray, so that's why this looks gray, but it's just showing that there's no color, so it's this colorless solution. And then it goes to being this blue. And then the copper metal here, instead of being this coppery reddish brown color, is now this fuzzy gray color. And so that gives us a couple of clues as to what's happening here. So let's start out by writing out our reactants here. So we have copper. Just ignore those stupid things that show up. I apologize for that. I have copper and this is copper solid, right? It's just copper wire, copper solid. And then I have silver sulfate solution. Now, silver sulfate. Silver is a metal, so if this starts with a metal, that means this is an ionic compound. If it's an ionic compound, I have to use charges and crisscross. Silver is Ag. What charge is Ag? Well, I know it's +1 because I had to memorize it that way. Sulfate. Sulfate's a polyatomic ion. You remember what it is? Sulfate is SO4 with a -2 charge. So now I'm going to crisscross those together. This 2 here tells me I need 2 Ags. So I need 2 Ags and an SO4. God. All right. And then this is aqueous because it's dissolved in water, right? All right, there's our reactants. That's what we started with, right? We started with copper, and it was a solid, and we started with some silver sulfate, which was an aqueous solution. And now we can see pretty quickly this is going to be a single replacement. How do we know it's going to be a single replacement? Well, I have an individual element here, just copper, and then I have a compound here, Ag2SO4. So this compound has 2 ions in it. The copper is going to try to replace one of them. Which one can it replace? Well, remember, metals can only replace other metals. So copper would try to replace Ag2. But how do I know that copper can replace Ag2? Well, that's what I'm going to have to look at my activity series for. So I'm going to go back to the activity series real quick. So I need to find copper and Ag. So here's copper. Here's silver. I can see copper is above silver here. So in other words, this is telling us that copper is more active. Copper would rather be part of a compound than by itself. Silver would rather be by itself than in a compound. Now look what we started with. Copper is by itself. We just said that copper would rather not be by itself compared to silver. So this can happen. Copper is above silver on the activity series. Therefore, it can replace it. All right, now that we've decided that it can replace it, we have to do the replacing. So now we know Ag is going to get kicked out by itself. Why is Ag just Ag and not Ag2 like it was before? Well, remember, the only reason it had a 2 here from before is because it was with sulfate that had a -2 charge. It's no longer with the sulfate, so you don't put the 2 with it. And then the copper and the sulfate have to go together. Now, this is the tricky part. What's the charge of copper? Are you thinking to yourself, well, I don't know. You're right, you don't know. I've never asked you to memorize copper because copper has multiple charges that it could be. Turns out the copper could be either +1 or +2. Right? Which one do we choose? Well, to tell you the truth, it doesn't really matter a whole lot. You could use either one and come up with the right answer here. Let's just say that copper +1 is the one that we're going to use this time. So if copper turns out to be +1, and you have SO4 -2 that has to go with it, well, now I need 2 coppers, right? If I do the crisscross. So this formula should be Cu2SO4. I have to balance this. Let's go through and balance it. I only have 1 Cu here, but I have 2 Cus here. That means I need 2 Cus. I have 2 Ags here. I only have 1 Ag here. That means I need 2 Ags. And I have an S, and I have an S, and I have 4 O's, and I have 4 O's. So everything else is balanced. Now the last thing I should do is go through and fill in the states of matter for these two. Now how would I know what the states of matter for these two are? Well, I wouldn't, except that they gave me a picture of what this looks like at the end, and so I can figure this out. Ag, well, Ag is silver. We know what color silver is, right? Silver is a gray color. Oh, so that must be this gray stuff that you see here, right? So that's the silver that has come out of the solution and taken the place of where the copper was. So now the silver is the solid, right? We can see that it's the solid here. And so the copper, since it's no longer the solid, the copper has now gone into the solution. The solution is now blue. What color are copper ions when they're dissolved in water? Well, guess what? They tend to be blue. So we know this is the aqueous solution now. Okay? All right. Double replacement reactions. Double replacement, remember, means that we're just having 2 partners here, and then they switch partners. Right? This is the one where you've got 2 people together, and then they're like, oh, I like your partner, and they switch partners. This one is probably the easiest out of all of them to figure out how to do because you're just switching their partners. Remember, this is an ionic compound, so this is my positive, this is my negative, this is my positive, this is my negative. So what has to happen when they switch? The positive has to go where the positive was. The negative has to go where the negative was. Okay? I'm going to erase all that crap because I don't know why that happens. Anyways. So double replacements, easy to figure out what the products are going to be. But you do have to keep in mind that one of the products has to be one of these 3 things. It either has to be a precipitate, which is a solid, right? Or it has to be a gas, or it has to be like a liquid, like a molecular compound such as water. So if one of these two here, if one of these two is not precipitate, a gas, or a molecular compound, then the double replacement reaction doesn't happen. Now, the gas and the molecular compound part doesn't happen very often, and we're not going to worry about those two situations, but the precipitate part actually happens quite often. But how do you know whether it's going to be, if one of these products is going to be a precipitate? Well, remember, precipitate means a solid from where there was no solid before. If we put an aqueous solution and an aqueous solution together, and then one of these turns out to be a solid, that means that the two ions that got together are no longer soluble. They can't stay dissolved in water. How do we know whether something can dissolve in water or not? We're going to use something called a solubility chart. This is also something that has been posted out there. It is also something that you may have a paper copy of, and you do not need to memorize these. The activity series and the solubility chart are things that I will definitely allow you to use on any test at any point. But how do we use this? So this is a series of rules that tells us whether ionic compounds are going to be soluble or not soluble. Okay. So for instance, it says that if you have a compound that has a group 1 ion in it, so any of the ions from group 1 on the periodic table, or it has ammonium in it, which is NH4 positive, then those ionic compounds are always soluble in water. So if you form something that starts with one of these metals or starts with ammonium, no matter what it ends with, no matter what its anion is, its nonmetal, it's going to be soluble in water. But then there are some of these other ones that have exceptions. For example, chlorides and bromides and iodides are soluble usually, unless they start with Ag or Pb or Cu or Hg. Okay. And they give you some of those exceptions. And then the same thing for the insoluble. Right? All common metal hydroxides are insoluble, except, and then it gives you some exceptions. So using these solubility rules, we can tell whether an ionic compound is going to be soluble or not. And once we figure out when one of the products is insoluble, we know that's going to be our precipitate. All right, let's see how this is going to go. Here's our practice one we're going to do. So this says we're going to take potassium iodide solution. You can see the potassium iodide is actually this one right here. It's really hard. I know it's kind of a blurry picture, but it's mostly colorless. Okay, it might have a slightly yellow tint to it, but it's mostly colorless. And then the other solution that we have here is lead 2 nitrate, and they didn't put that in here. I'm going to put that in here. Okay, so this is lead 2 nitrate. It's also a solution, aqueous solution. It's dissolved in water and doesn't have really much color at all, so it's colorless also. So I have potassium iodide solution, lead 2 nitrate solution, and I'm going to put them together into the same beaker. When you put them together in the same beaker, you get a precipitate. In fact, a bright yellow precipitate. Look at all the solid that formed when you put those two together. Okay, so we're going to, again, we're going to put those two together, and we're going to try to figure out what that precipitate is. All right, so let's write this out. So potassium iodide. All right, so let's see. That's potassium K. K is a positive 1 because it's in group 1. Iodide, IDE. That's usually just a singular nonmetal, so that's just I. It's in group 17, so it's negative 1. So if you put those two together, K positive 1, I negative 1, well, that's easy. You just need one of each, just Ki. We said that's dissolved in water, right? So that's aqueous. All right, lead 2 nitrate. So lead is Pb. What's its charge? Well, it has a 2 here. That's the reason I gave that to you, because you wouldn't know what the charge is otherwise. So we know that the lead must be positive 2. Nitrate, right? That's one of those polyatomic ions that we should know. NO3 with a -1 charge. So when I crisscross these two together, this tells me I need 2 of those nitrates. So this is going to be PbNO3 2. Okay? And that was an aqueous solution also, right? That's what it showed us here at the beginning. All right, now this is going to be a double replacement. Again, how do I know it's a double replacement? Well, this has 2 ions in it. This has 2 ions in it. So now the ions are going to switch partners. Remember, the positives and the negatives are going to switch partners with each other. So I always think of it as just the positives switch places. So the K positive is now going to go over here, and the Pb positive 2 is now going to go back over here. So now I have to re-crisscross. So K positive goes with NO3 negative. So that's +1, -1. I just need 1 of each, right? So just KNO3. And then the Pb positive 2 is going with the I negative. That tells me I'm going to need 2 I's. So that's PbI2. I do have to balance. Every time you do one of these, you've got to balance it. So let's start with the K's. I have 1 K here, I have 1 K here. That worked. I's. I have 1 I here, but I have 2 I's over here. So if I want 2 I's, I have to put a 2 in front of the Ki. Oh, wait, that gives me 2 K's now. So now my K's aren't balanced. Now I got to go back and do the K's. So I need 2 K's over here. All right, that's good. PB's. I need 1 PB here. I have 1 PB here. I'm good. This tells me I need 2 N's. Well, this is 2 N's. And then this is 6 O's. Well, this is 6 O's. All right, so that's balanced now. Last thing, I got to figure out which one of these is that yellow precipitate. So the way I'm going to do that is I'm going to go to my solubility chart, and I'm going to look up both of these on the solubility chart and see if it tells me which one of these is insoluble. Let's start with this one, KNO3, potassium nitrate. Let's go back. Let's look up potassium nitrate. So you could look this up 2 ways. You could either look up the potassium part or the nitrate part. Rule number 1, all common compounds of group 1 ions, which includes potassium, are soluble. So even if I just ignored the nitrate part, just knowing that it starts with K tells us it's soluble. But let's say I just accidentally forgot to read number 1 and I skipped to number 2. Number 2 says all common nitrates are soluble. The fact that it has nitrate in it also would have told us that it's soluble. So either way, I know this is soluble. When it's soluble, that means it does dissolve in water. That means it stays dissolved as an aqueous solution. That's not my precipitate. This is obviously going to be the precipitate, but let's just make sure by going back and looking it up. So this is lead 2 iodide, right? Lead 2 iodide. Lead 2 iodide. Here's iodides, right? Number 3 says all common iodides are soluble, except lead 2. So in other words, lead 2 iodide is not. It's insoluble. So it must be the precipitate. Precipitates are solids, so I'm going to write solid next to it. Now, what if PbI2 was soluble? What if it was aqueous? Well, this would have started off as 2 ions dissolved in water plus 2 ions dissolved in water. It would have made 2 ions dissolved in water plus, and if this were aqueous, this would have been 2 ions dissolved in water. If that ever happens, that means there was no reaction that could have happened. Why? Because nothing changed. If we started off with 4 ions dissolved in water and we ended up with the same 4 ions all dissolved in water, then they didn't do anything special. You have to have, remember, you have to have one of those 4 signs of chemical reaction. You have to have a color change, or a temperature change, or the production of a gas, or the production of a precipitate. Right? There has to be one of those four things that happens. All right, last type of reaction we've talked about in here is called a combustion reaction. The only type of combustion reaction that we have to be aware of for this class is the combustion of a hydrocarbon. So in other words, if you see a compound that has C's and H's in it, and you're adding it to oxygen, that means you're burning the hydrocarbon. If you burn a hydrocarbon, you always make the same two products, CO2 and H2O. This actually becomes a really, really easy type of reaction to figure out. So if I started you off with CH4 plus O2, gosh, and I wanted you to go through and figure out what the products were of that, well, it would be really easy. You would know immediately what two products you're forming. There's no replacements to do. There's no trying to figure out charges and crisscrossing and all that kind of stuff. Your products are CO2 and H2O. Okay? That's it. That's all it is. You don't have to do anything else. You may have to balance it. But outside of balancing, that's the only thing you'll have to do. So these are the easiest ones to do. Hydrocarbons plus oxygen always gives you CO2 and H2O. There you go. There's an example of one, right? Anytime you see something that's burning, it's almost always a hydrocarbon. A candle has this cotton wick. Cotton is a natural material that's made out of lots of different carbon and hydrogen compounds. So we have a hydrocarbon here that is giving off light and heat. But remember, light and heat are not things that we put into our chemical reaction. So what are the other things that are coming off of this reaction? CO2 and H2O. Can you see CO2 gas? No, that's why it doesn't show up in this picture. Can you see H2O gas? No, but it is coming off. Those are two products that are happening. Every time you burn a hydrocarbon, those are the two products that we're getting. Okay? All right, so that's the 5 types. The only way to get good at this, I know there's a lot of information there, is to practice it. So there are several of them to practice in your homework.